Hi guys, I'm Tim and today I'll be speaking through my project. As you can see, trying to develop an empathy mechanism for AI agents. So here's the overview, but I think we'll probably just jump straight into things. So good place to start is with the motivation for our research project. So yeah, the core question we're trying to get at here is, can we develop more robustly cooperative AI agents? So what does robustly cooperative mean here? So basically what we mean here is agents that can navigate social environments in a cooperative and pro-social manner with both humans and AI agents. So for example, by social environment here, we mean like you might consider self-driving cars on a motorway. There's a lot of social interactions that go on there. Imagine you have to overtake a car. There's pedestrians on the sideway. There's a lot of social stuff that you have to keep in mind. So we want our self-driving cars to be cooperative. Or you might just consider like a trivial example of like a personal assistant. Of course, you want them to cooperate with you, with other personal assistants. Yeah, a lot of daily problems are cooperative problems. So second thing we want to get at here is trying to better understand the personal inductive biases that promote cooperation at a group level, especially for agents with different power or influence. So what do we mean here by inductive biases? So we generally mean like the human social capacities that we think are kind of relevant for cooperation. So you might consider like imitation, like being able to imitate other people, generally useful cooperation, or our kind of innate sense to punish free riders. Another kind of inductive bias that's good for cooperation on a group level, or so we think, or empathy. So that's what we're going to try and get at. So yeah, I guess first of all, what do we mean by empathy? You can ask yourselves this question. It's might be a loaded term, but when we speak about empathy in human discourse, we generally mean two things. So first of all, we mean kind of just understanding the preferences of others. So putting this in practical terms, you might be having a thoughtful conversation with a friend. If that friend can simply just understand how you're feeling, put yourself in their in your shoes, we'd consider that to be an empathetic person. Yeah. So second thing we mean when we say empathy is valuing and acting to increase the preferences of others. So that friend you're having the conversation with, if they now act on their understanding of your preferences and do something to help you, that's also empathetic. Another trivial example might be someone carrying something heavy. You have to first understand that person might not want to carry that heavy thing and might want a hand. And then second part of that, go and actually help that person carry that heavy thing. So yeah, this is what we mean when you say empathy. At this stage, it's also useful to go over some glossary terms. What is reinforcement learning? So, and how does it differ from like typical machine learning? So the way I like to think about this is machine learning is about seeing, whereas reinforcement learning is more so about doing. So a typical machine learning model, supervised or unsupervised, it'll be passively kind of fed data, and its task is to find patterns within that data, find the best fit. Whereas with a reinforcement learning agent, it actively takes steps to generate the next data rather than being passively fed the data. So yeah, and what's multi-agent reinforcement learning? This is kind of the next step of that. So we have multiple reinforcement learning agents acting out in the same environment and interacting with one another. And yeah, another glossary term, what are social dilemmas? So these are pretty key to our question here. And the most famous example would be the prisoner's dilemma. So just to put this, just to play it out for you. So let's say we have two gang members and they're arrested by police and they're placed in individual cells because they've been imprisoned, but the police don't have that much evidence on them. The police will offer might offer these gang members this kind of ultimatum. They'll say, if you cooperate or if you defect on your other gang member, we'll let you go for free, but your other gang member will be in prison for 20 years. But if you both do this, you'll both be in prison for 5 years. However, if you both cooperate and don't say anything, you'll only stay in prison for, let's say, 1 year. So the figures here are somewhat arbitrary, but the main thing here is that the optimal individual strategy is to defect, whereas the optimal long-term group strategy is to cooperate. So it's kind of these scenarios where individual rationality can lead to group irrationality. So yeah, there's lots of real world examples of this. You can generally model like climate change, for example, as a cooperative problem. So countries around the world need to cooperate, reduce their carbon emissions, invest in renewable technologies, and this might take a slight hit to their economic growth on a personal individual level. but countries have an individual motivation to maybe ramp up their emissions in a bid to grow their economy, etc. And there's lots and lots of social dilemmas every day. So yeah, getting back, what are we trying to do? We are trying to develop more robustly cooperative AI agents. So how can we test this cooperation? So yeah, we're testing it in social dilemmas. So these AI grid worlds that have the same dynamics of a social dilemma. So these are 2D grid worlds. Yeah, we've got two of them here, harvest and cleanup. So harvest is a tragedy of the commons dilemma. So agents are personally tempted by basically to deplete a shared resource by all. So what that means practically here is there's apples in this environment, and agents are motivated to eat as many apples as they can fast as possible. But if they do that, there won't be any apples left and the apples won't regrow. So there's a fine balancing act here. And the cooperative thing to do is abstain from eating lots of apples. Cleanup is a public goods dilemma. So agents must pay a personal cost to provide a shared resource by all. What that means here is the agents have to clean up waste in the river in order for apples to regrow. And the hard thing here is to clean up the waste, because otherwise agents can be lazy, defective, and just hang around where the apples are regrown, just eat apples and not really do any work. So yeah, this is how we're going to test cooperation. So previous methods. So standard reinforcement learning algorithms fail at these environments. And these are reinforcement learning algorithms that are state of the art in single agent reinforcement learning systems. They learn defective, selfish strategies, and they just generally don't work. So there's some extra methods that do work in these environments. And two recent examples are papers where they designed agents that have inequity aversion, and then also agents that are rewarded for causal influence. So in the inequity aversion paper, as a team from DeepMind, they designed agents that basically they designed agents with an inequity averse preferences. So agents had to balance a selfish desire for individual rewards against the need to keep deviations between their personal rewards and others similar. So basically, all the agents had to have the same reward in order to kind of work and not get punished for it. And the causal or downside of this is that it could result in guilty agents. So it only works if every agent has this inequity averse preference. Otherwise, if there's one agent who doesn't, they can just exploit everyone else. So it only works under certain environments. Another paper rewarded agents for having causal influence on other agents. So what does causal influence mean? It just means rewarding agents for having high influence on the actions of other agents. So basically got agents to ask themselves, how do my actions affect the actions of other agents? So this is largely what our paper is based off of. And I guess a common caveat here is not all causal influence is good. So this worked really well. But it worked really well because in the environments that they were tested, cooperation is the hard thing. And you can imagine agents can have a really high causal influence on other agents in a not cooperative way. So for example, an agent could also have a high causal influence by just getting in the way of other agents or coercing them. And that's not good. And yeah, all methods also failed or struggled with the lazy agent problem, basically where you had free riders or agents don't learn to just do anything. So yeah, our method, we assume we have access to other agents' value functions, and this is one of the assumptions. And then we reward agents for having an influence on the reward received by other agents. We do this using counterfactuals, and you can think of this as a sort of empathy. So practically speaking, we just add a term to agents' loss functions. And this term is basically calculated by getting the agent to ask themselves, how did my actions affect the value functions of other agents? And we reward the agent for having a strong influence on the reward received by other agents. And the hope here is that this will lead to emergent altruistic behavior. So where are we at? We've implemented the environments. It's probably worth noting here that DeepMind doesn't open source the code. So we spent a lot of time just kind of catching up. We've got harvest and cleanup. Those are GIFs, but I don't think they're going through, but the agents move around and they do work. We've got the standard agent baselines matched. So these are like the selfish agents. They're the baselines, they're matched. So we'll be, going forward, we'll just be implementing the actual reward influence and see does it work. So yeah, going forward, implement the reward influence. There's a couple kind of key questions we also want to try and figure out. First of all is, how does the agent or behavior of an agent with the reward influence differ from basic agents, especially environments where agents have different levels of power or influence. So I guess the core question is here, does cooperative behavior stay stable on the way to superintelligence? We can't obviously test that fully, but we can test that at least partly empirically by giving agents in these environments kind of different power or influence, and yeah, seeing what behavior emerges. Yeah. And the other core question we want to ask is, well, I guess going back to what we mean by empathy, understanding the preferences of others is really important too. And right now we're only addressing the second. We're just giving the agents free lunch by assuming they have access to other agents' preferences, value functions. But yeah, a core question here if we're going forward would be, yeah, getting the agents to actually learn the preferences of other agents rather than just giving it to them for free. This would be pretty important, and it's a hard but exciting problem, so should hopefully be fruitful for going forward. And yeah, might involve merging with inverse reinforcement learning. Not 100% sure at this stage, but yeah, going forward should be exciting. So yeah, that's everything. I guess we can get on to questions. I guess I'd just like to say thank you to Tim, Christian, Ivana, and everyone at the CERI offices. Yeah, thank you.